Chapter 16, Vector Calculus. We're going to start with 16.1, Vector Fields. Now, if you recall in Chapter 13, we actually covered vector functions. Those are functions that assign a vector to a real number. And we saw that vector functions of real numbers are useful in represented curves. In fact, it's pretty much the only effective way to represent curves and motion, and especially motion along that curve. Now we're going to go ahead and take a look at two other types of vector functions. Functions that assign a vector to a point in the plane or a point in space. And these are actually called vector fields. And as you'll see, not only in this class, but in a typical physics class and beyond, this is very useful in representing various types of force fields and velocity fields. First, let's start with the definition of a vector field. Definition of a vector field. Over a plane region R is a function f that assigns a vector to each point. Or you also have a vector field over a solid region. Yes, vector fields can not only be two-dimensional, they can actually reach out to three-dimensional solid regions. And again, it's a space such that a function f assigns a vector to each point in the solid. Now for those, you generally want to use a computer-generated image. It's pretty hard to do by hand. Almost impossible, actually. In fact, it's already very difficult to do a vector field in a two-dimensional plane. But we'll give it a shot. And for your next exam, I will likely ask you to sketch a vector field by hand, so that will definitely need to be practiced. In your homework, you'll notice, though, that many times they'll just go ahead and present to you an option of, let's say, four to six vector fields to choose from, and you'll need to correct you'll need to correctly choose which vector field is represented. But on a test, you actually do need to sketch these out by hand, as I'll mention more later. Now, as I said, another type of vector field is a force field, and it associates a force vector with each point in a region. So a good example, as I'll talk about more later, and it's in your book, is a gravitational force field. Now, in general, a vector field is a function whose domain is the set of points in R2 or R3. But again, because they assign vectors to each point, domain is a set of points, range is a set of vectors. Okay, and here's the formal definition that you can find in your book. Now, this section isn't really that difficult. It's more just tedious. And again, you'll need to practice these vectors by hand. But I'm going to go ahead and give you a few examples here that hopefully can show you how to do the problems in a fairly easy manner. Start with the first vector field. We're going to go ahead and sketch this. Now, we all should know how to sketch vectors at this point. And really, all we're going to be doing is plugging in values of x and y here. Okay, plugging in values for x, plug in values for y, then plug them in here. And the point is that a vector has a beginning and an end. It has a tail and a head. And the point is that whatever point you decide to plug into this vector field, you need to represent it in the vector field sketch based off of the fact that it is going to be, the vector will begin at whatever point you choose. Okay. So I know many vectors start at the origin, that would be standard position, but in a vector field, your vector must begin at the point that you are, the point in question, the point that you are actually beginning to draw the vector from. And if that was a little confusing, it's okay. I'll explain more later. Now, two things you must consider. One is the location of where the vector begins, and I just mentioned it's the point that you choose. So whether the point be 1, 2, or negative 5, 3, or whatever point you choose. But you also need to consider the magnitude or the length of the vector. So the length of the vector in this particular case, pretty easy to see. We should be good at this by now. All we simply have to do is square the I term and add it to the square of the j term. Will be the magnitude, as we've known from previous sections. So this also needs to be kept in mind. And for a problem like this, I'd rather just show you the entire solution and kind of talk to you about it piece by piece. So this is the solution to the entire problem. It says sketch the vector field, so really the answer is just simply going to be this portion right here on the right side. And I'm going to kind of explain to you how I got this, how this was generated. Now, because my force field is represented by the expression xi plus yj, and we also know that the length the magnitude of each vector is actually going to be this here, the square root of x squared plus y squared. This should be very familiar to us because the magnitude here, this is a very special magnitude. They will not always be this magnitude. Each vector field has its own magnitude for their vectors. But this should look very familiar to us. In fact, this expression here literally is simply just the distance from 0, 0 to xy itself. And that should be pretty obvious to see. And the reason why that's obvious is if you just use a basic distance formula from any typical algebra class, you would end up with x squared plus y squared inside of a square root. And also, each vector happens to point away from the origin. Now, these are just observations that you can make as you build this vector field. You might be wondering why this is true. So for example, I'll just kind of give you an idea of what's happening here. So let's take a look at this first. Let's take a look at this vector here. Let's just kind of let that vector there be our focus. So as I'm focusing on this vector here, let's go ahead and just kind of pretend that this is the point -1, -2, up 1. Okay, let's just pretend that's what that is. Okay. Well, if that's -2, -2, 1, then all you simply do is you take this vector field here and literally replace whatever coordinates you have here into the vector field itself. So you'll notice over here, I'm going to go ahead and replace x with a -2. I'm going to replace y with 1. And literally, this vector right here is the vector -2, 1. Now again, these are not in standard position. These do not begin at the origin. They begin at the actual point in question. In this case, this is the point -2, 1. In fact, to further illustrate this, notice that if I just simply recreate that vector from the origin in standard position, as you can see here, it just basically, and you're welcome to start there if you wish, but then eventually it must be moved to where it's supposed to actually be, which is starting at the point -2, 1. And again, this is the actual vector. Notice the vector brackets here, represented by this arrow over here. Let's try another one. Let's say we had another vector. Let's focus on another one. Which would be a good one? Let's let our next one be this guy. Okay, let's focus on that one now. Okay, so I would say this point is like what, the point maybe -1/3, 1 would be this point. Okay, so let's look at that point now. So since we're going to focus on that point now, let's plug in the numbers here. So again, we'll replace x here with -1/3. And we're going to replace y here with 1. So that's going to lead me to the vector -1/3, 1. Which is represented by this vector here. Now, once again, you are welcome to start at the origin in standard position and then slide it into where it's supposed to go. But keep in mind, again, that this vector here is represented by what you see here, okay? And you also can find its magnitude or its length. Notice that it's shorter than the first one I actually dealt with. It's because it's just in a different position. It's actually closer to the origin. In fact, you'll notice the closer we get to the origin, like let's say if I wanted to sketch any vectors that are closer and closer to the origin, you'll notice that these vectors get shorter and shorter and shorter. And just by nature of this vector field alone, each of the vector points happen to just point away from the origin. It's just by the nature of this particular vector field. Okay. Now I invite you to try to sketch some more vectors yourself. I'll go ahead and sketch one more vector for you, like a random vector. So I'll pick a random point and go from there. Okay, so let's go ahead and try the point -5, 2. -5, 2, the vector at -5, 2 can be represented with -5 I hat plus 2 j hat, or it can also be represented with vector notation with the vector brackets. So let's go ahead and sketch that. First, we go ahead and plot the point -5, 2. And from that point, we're going to follow our vector, which in this case is left 5, up 2. It's not a perfect line, but you get the point. This is how you sketch just one of the vectors in this particular vector field. Once again, notice it has the same nature. It follows the same distance from the origin to the point itself is the length of the vector, and again, it points away from the origin. Let's go and do another one. Again, I think it's best for me just to show you the entire solution and then maybe point a few things out and also sketch one or two vectors for you. So obviously for this one, the length of the vector of each vector in this vector field is going to be the quantity y squared plus 1. All you simply do once again is square the first component and square the second component, or yes, and then put it into a square root. Now in this particular case, the nature, now again, this is just a observation. The vectors in this case are tangent to parabolas opening about the x-axis. And obviously, as you can see, they look like families of parabolas. Now, I'm not going to ask you necessarily to look for those key facts or those the nature of each vector field, but it is sometimes helpful to see. Now, why don't we go ahead and sketch one of our own? So let's go ahead and do the vector at 1, 4. Notice that the y component always comes first. So whatever the y coordinate is of your point, that will always come first and become your I vector here. So in this particular case, let's go ahead and first start by plotting the point. Remember, we're plotting the point 1, 4. So there's the point 1, 4. And from that point, we're going to go to the right 4, up 1. Again, not a perfectly straight line, but that would be our vector at that point nonetheless. And hopefully that makes sense. Now again, looking at any one of these vectors here hopefully makes sense to you. Let's take a look at one that's already established. Let's take a look at one of these guys down here. How about this one right here? Let's take a look at this one. So again, you want to put your point where this vector begins. And to me, this looks like this goes to the right, 1, 2, and maybe even one more, 3. Goes to the right 3. And down 1, 2, let's say. And maybe this is not quite to scale, but it's close enough. So again, this point to me would be the point 3, negative 2. So if I plug the point 3, negative 2 into our vector field expression here, we would end up with the following. So does this vector that's being shown here, does that make sense? And I think many of you could already see that it does make sense, because if you notice, the vector is asking us to start at this point 3, negative 2, and the actual vector itself from that point 3, negative 2 is going left 2, up 1. So that kind of makes sense to me. 1, 2, up 1. That looks about right. Now again, this is not to perfect scale, but it gives you the idea. Let's go and do one more. This is a very easy one. Notice that there are no variables in this particular one. Like I don't have x, j, y, k, whatever. And also notice that it's 3-dimensional. Now this is a pretty crazy one. And typically when it comes to a 3-dimensional vector field, you'll want to use some sort of computer-generated image. And you'll notice in your homework that there are a few of those where there's some computer-generated images to help you, and you just basically got to choose the right one. I might even do that on an exam, is generate some computer-generated images for your benefit on an exam, and you just got to pick which one is correct. So you'll get some practice with that in the homework. This one is not so bad. It is 3-dimensional vector field. However, you'll notice that I'm only providing for you guys 2 components of this 3-dimensional vector field. Well, because of that, we're going to get a very, very simple and basic vector field. In fact, it's going to whittle it back down to a 2-dimensional one as follows. Now, it's obvious, though, that the magnitude of each of these vectors is simply just what? You just simply, again, square all the components, add them up, throw them into a square root. In this case, I think it's pretty easy to see why the magnitude of each one of these is square root of 2. And notice here in this particular case that I went ahead and showed you what a vector field looks like in a YZ plane. Okay? Because every parallel plane to this, where x equals whatever constant you wish, it's going to look exactly the same. And furthermore, notice that this vector has no variables once again. So that means every single one of these vectors will have the components 1, 1. And you'll notice this is true. Any point I have here, you're going to have a vector that starts at whatever point you are trying to create a vector at, and it'll go right 1 and up 1. So let me go ahead and do another one. So let's say I had one up here. So if we start at this point, again, it doesn't matter what point it is, but this point happens to be 2, 2. Again, it doesn't matter. We're still going to go right 1, up 1. And as you can see, we end up with basically the same vector. Again, not perfect, but you get the idea. So you can see how tedious these get. And I'm not going to really be focusing on this section all that much. However, it is important to know, and it is good to get a good, basic idea of what to expect from this section. Now in the homework, typically I will give you computer-generated images. You choose which image best explains the situation. So really, this is kind of like a typical example of what you can expect. So let's go ahead and look at what we have here. So the question here asks us to match the vector fields with the plots and then give reasons. And I'm just going to talk about this with you. I'm not really going to go through into too much detail. Let's start with this first vector field here, A. Which one of these pictures matches with this vector field A? Vector field A here, this actually matches with graph 3. And the reason why it matches with graph 3 is because if you take a look, notice what's happening here. Just kind of like, basically think through this logically. As we move to the right, notice how the vectors just seem to be getting bigger. It's the same thing, as we move up, the vectors seem to be getting bigger. In fact, both the x and y components are getting larger as we move up and to the right. Okay, as far as magnitude is concerned. Okay. Well, as you move up and to the right, the magnitude of either one of these components are going to get larger. So again, don't forget, what's magnitude? You square this component, you add it to the square of this component, and then you throw it into a square root. Of all three of these vector fields, well, actually with the exception of one of them, but I'll explain more in a moment, that's essentially what's happening here. Furthermore, you can even just kind of like pick a random point on this graph and just go ahead and sketch the vectors themselves. Now, I will point out one thing though. When it comes to computer-generated images, sometimes even what you see is not to magnitude or to scale. For example, notice how I'm getting close to the unit of 5 here. Well, let's say we went to and this is also 5 up here. So the point over here would be 5, 5, right? Basically. So what would be the magnitude of that? The magnitude of that would be 5 rad 2, which is actually pretty long. It's like, it's a very long vector that's going to be shooting off the charts here. So how come my vectors are so small here? Well, it's so small here because you need to find a way to represent this efficiently, and that's just how they found a way to do it. So even though physically these vectors are not the length that they should be, again, the vector here on the corner is shooting off the charts here, and the one right next to it is super tiny. Yes, that's not to scale, but if you look at it proportionally, this vector here this vector here is proportionally accurate compared to this vector closer to the origin. So once again, go ahead and try plugging in some points, and you'll get vectors that shoot off the charts. But as long as they're going in the same direction, and as long as the proportionality is accurate, then that's going to make this graph 3 obvious as the obvious choice for part A. Okay, part B now. Which one is a good graph for part B? Well, part B has sine x, sine y. Okay. This choice for part B corresponds to graph 2. And there's one obvious way to notice how this is true. Notice that I have scales of 6 this time. Now, scale of 6, again, when we're dealing with trigonometry, just kind of use our common sense here. That essentially means that they're talking about 2 pi. Now, 2 pi is bigger than 6, obviously, but they're just trying to be convenient. And then, obviously, smack dab in the middle is basically going to be pi, right? So this will be pi. So if this is pi, that means up here is also pi. So if we look at the point pi pi, notice that we have essentially a vector that has no length at all, or it's very tiny. In this case, it's probably going to be no length at all. And that should make sense, because if I plug in a pi pi here, sine of pi is 0, sine of pi is 0. So to me, that makes it the obvious choice. Again, please feel free to plug in other points to verify, but this to me is why that makes perfect sense. The vector field B here is corresponding to graph 2. Which finally brings me to the part C here. Part C, obviously, by elimination, corresponds to graph 1, and really, the main thing I want to point out with this is that if you'll notice, a couple things I want to point out is that notice that this first component here, right here, this first component, ln of the quantity 1 plus x squared plus y squared, is always positive. So because this is always positive, and notice it's also the x component of my vector field, notice that every single one of these vectors up here, every single one, they're all moving to the right. None of these vectors are moving to the left. They're all moving generally in the positive x direction. Okay? Whereas notice my second coordinate is just x. And so that obviously can take on positive and negative values. So notice that I do have some vectors that are going downward, some are going upward. But the main idea is that since the first coordinate here of my vector field is always positive, notice that all my x components for every single one of these vectors is moving to the right in the positive x direction. So that was the giveaway for that one. So even if it wasn't by process of elimination, that to me is the giveaway. Now the remainder of this section is a lot more of the same, but there is one more key aspect I would like to point out. And the fact that we are dealing with vector fields is going to go a long way for the rest of the semester. So getting a basic introduction to it is a good idea. But essentially, one other example of a vector field that's going to be incredibly important is the gradient. Now we've already dealt with the gradient in this class. We actually had quite a bit of we have quite a bit of experience with the gradient in this class. So for example, let's recall, we should know this already. What would be the gradient of this function here? The gradient would be, okay, again, don't forget, what is the gradient? Well, the first component of the gradient is going to be the partial with respect to x. The second component of the gradient will be the partial with respect to y. This should not become of any surprise to you. So therefore, the gradient is, in this case, 2xy plus 3y cubed, plus the quantity x squared plus 9xy squared, j. Again, that should come as no shocker to you. So what's new is that even though you know how to compute the gradient, what you didn't know is that all along, the gradient is also a vector field in the plane. Now, in similar fashion, we can extend this to three variables and beyond. But for example, the gradient or the vector field, I should say, for x squared plus y squared plus z squared is 2xi plus 2yj plus 2zk. Again, that is another vector field. So having said that, all you simply have to do to find the vector field of any function of 2 or 3 variables is simply to compute their partial derivatives in their proper components. So let's just do one very quickly. This is a very simple part of this section. So for example, the gradient vector field for f in this case would simply be 3e to the 3x cosine 4y, because we took the derivative with respect to x, leaving the cosine 4y constant. And secondly, for the second component, we take the partial with respect to y, which in this case, e to the 3x is held constant, and we're left with not only negative sine 4y, but also multiplied by the chain rule factor of negative 4. So I really don't think there's any problem here. This is going to be a very simple aspect of this section. Also, the gradient vector field of f, in this case, you can, like I said, extend it to 3 dimensions and beyond. So I would ask you to pause the video here and see if you can actually come up with the gradient vector field yourself. And in this case, it would be y squared is the first component, 2xy minus z cubed, second component. Third component is negative yz squared. Another very important aspect of a vector field, this is going to come into play later in the chapter. This is very important, this fact that we're about to see here. So I'm just kind of introducing it now, but in subsequent sections, this will become more and more of an important item, so please take note. A vector field is what is called conservative, a conservative vector field. If the gradient of some, if it is the gradient of some scalar function. In other words, if there exists some function f such that this equation is true. Now, right now, you might not really understand what this means, but this is going to become an incredibly important fact in the coming sections. Once this important fact is established, this situation is going to allow for us to identify a potential function for f. Again, another important fact. So as to kind of keep this in the back of your mind, this is going to follow us for the rest of the chapter, which essentially is the rest of the semester. So please keep this in mind. Again, it is going to be conservative if we can find some sort of function, potential function, where this is true. But more on that later. Now, there are many important vector fields, including gravitational fields, electric force fields. Those are conservative. Several of the concepts from this section actually comes from physics. Case in point, the word conservative, if you have taken a physics class, you've probably seen that word several times. It's derived from the law of conservation of energy. This law states that the sum of the kinetic energy and the potential energy of a particular particle, moving in a conservative force field is constant. And so if you've taken a physics class before, you actually probably already know this. As I mentioned earlier, and this is in the book, please read example 4 from the book. It details the gravitational field, and even has an expression here. So I recommend you read that. This is just one example of a conservative field that I would like you to take note of. So finally, let's go ahead and find the gradient vector field and then sketch it. Essentially, what I'm about to show you is you already know how to do this because you know how to find the gradient. That's going to be easy. And then once you find the gradient, you're simply going to sketch it. And how do we sketch it? Well, I gave you 3 examples earlier in this section on how to sketch vector fields. So essentially, I can almost stop it here. In fact, I would invite you to once again pause the video here and you go ahead and do this problem yourself. You do not need to watch the solution to this to figure this out. All the elements of how to do this problem here has been detailed in this section already. So again, I would invite you to pause the video here and try to do this problem yourself. Assuming that you paused it and now that you want to see the solution, let's proceed. The gradient is the easiest part. Take the partial with respect to x for the first component, take the partial with respect to y for the second component, and we end up with 2xi minus yj. I don't think there is any objection there. Also, very important, not only do we need to sketch each vector, we need to sketch each vector to match a specific magnitude. So the magnitude of each vector in this particular case is going to be 4x squared plus y quantity squared inside of a square root. I don't think there's any objection there either. And go ahead and try to sketch this yourself. Now again, try to pause the video, sketch a few vectors by yourself. It's always best to try these things by yourself. If you only wait for people to, or someone to give you a solution, you're not really letting your brain cook a little bit. So please try to sketch a few of these vectors yourself. It is tedious, it's annoying, but trust me, you should practice, because if I ask you to sketch a vector field on the test and you don't practice, you will fall flat on your face. And it's not hard, it's just tedious. It takes some discipline and some just some patience. And trusting that you went ahead and paused the video and tried to sketch some of these vectors yourself. Here is the vector field in this particular case. Now, I'm not going to require this from you, but there's a fun fact about this particular vector field. You'll notice that every single one of these vectors, whether it starts up here or down here, here's the point 1, 1, over here, here's the point -1, -1, they all actually end at some form of point here. Every single one of those vectors end up at a form of 3x, 0. If you don't believe me, go ahead and plug in any one of those points, and you'll notice that they may start up here, for example. Here's the point -1, let's say 3, right? Well, if I plug in -1 into this little point here, I get -3, 0. Well, this point starts at -1, 3, but ends at the point -3, 0, as an example. Now, I'm not requiring you to know these fun facts about these vector fields, but if you can actually notice how these vector fields behave, then drawing these vector fields become much more efficient, much quicker, and a little bit less, a little bit less of a headache.